Hello, this is session 19. We're considering pages 302 and 312. We're talking logarithms today, and as usual I have at the top, log is an exponent. Most important to realize that a log is an exponent. So all the rules for exponents will also apply for logs. First we need a definition, and the definition we have is that, in fact this is from the book, y equals to log base b of x implies, or is the same as, x equals to b to the y. I like it better with something that I've adopted, log base b of n equals to e. B stands for base, it's written lower, n is the number, and e is exponent. Remember here, log is exponent. Log is or equals exponent. So this base raised to this exponent equals to that number. Base raised to exponent equals to number. I like that a little bit better than what's given with x and y above there, but your choice either way will work, it's the same thing. The rules follow here. The first rule is that the log of the product, when you're multiplying two numbers, let's consider that, multiplying two numbers here. If we're multiplying x squared times x cubed, what do? When we're multiplying with the same base, you keep that base and add the exponents, don't you? You add the exponents. Okay, so when we're multiplying with the numbers here, what are we going to do? The base understood to be b, or in this case, if there's no base, understood to be 10. We're going to say when we're multiplying with the same base, multiplying with base 10 there, we'll add the exponents. So this log of xy becomes log x plus log y. The same thing for division. If we're dividing, for example, let's say we're dividing x3 by x squared, but we go ahead and keep the base and subtract the exponents. Same thing for the logs. Log of the division, sometimes parentheses are placed around this to make it more obvious. It doesn't make any difference one way or the other. But if we're dividing those numbers, it's the same as subtracting the log. So log of x over y, same as log of x minus log of y. Taking to a power, let's consider taking to a power for a moment. If you're taking to a power here, maybe x cubed squared if you would. We're going to keep that base and keep base and do what? How about multiplying, okay? Keep base and multiply the exponents. We'll do the same thing here. When we're taking to a power, we're going to keep the base and multiply the exponents. Now, y is an exponent by virtue of the fact that it's raised, and of course log of x is an exponent. So we're going to say then that log of x to the y is the same as y log of x. A little dot in there if you would, a multiplication situation. We also have what's called the change of base routine, or base of change procedure, that change of base procedure, that if we have here the log base x of y, that can become log of y over the, or divided by the log of x. Doesn't sound right. I'll show you why that's the case when we get to a problem involving it, okay? Kind of a nice, easy procedure to play with. Rather than going through all of the math of it, we can just make a simple change like this. And you'll see why that's true. I don't want to just say take on faith here. Two other corollaries that we should know, that log of 10 is 1 and natural log of e is 1. Log of 10, remember this is base 10 understood. Base 10 raised to the first power, or 10 to the first is 10, that's certainly true. This natural log of e is log base e. So what we're going to say is, we're going to say down here maybe that log base e of e is equal to 1. Natural log is the same as log base e, and that's certainly true. E to the first power is in fact e. E is our natural number again, 2.71828. Playing with that a bit. Those are the rules we need. Ask you also to do this, please. Print the log and the e tables. You need those for this session. And those come from the Canvas files, okay? They're there for you. I have a nice packet that I was prepared to give you in pink here. Unfortunately, I wasn't able to do that, so these are back to back. In your case, you'll probably have to print off individual pages there. But do print off both tables, the common log table and the natural log table, as well as the e table. Okay, you'll need those. We're beginning with page 302, and 302 says, how about changing from one form to the other? We like to change from the log form here to the exponent form. And the reason you know it's log form, really simple. How about log, okay? There's an log here, meaning it's log form. We like to change it back to the exponent form. And your author does a nice job of starting with log form. Some authors start with the exponent form, and then they say change to log form. You can't check that too well. In this case, starting with log form, you can really check it very nicely to see if it's true. Log, the way it's said now, log base 2 of 1 over 32 equals to negative 5. Or another way of saying it, the log of 1 over 32 with base 2 is equal to negative 5. Either way, we're going to proceed to change this to say this is the same as the base 2 raised to the negative 5 exponent. Log is an exponent raised to the negative 5 exponent should be the number 1 over 32. And as I say, the reason that the author does a good job here is because now we can check this. Is 2 to the negative 5 actually 1 over 32? I think so, isn't it? Remember, the negative sends it to the opposite area. This should be 1 over 2 to the 5th. 2 to the negative 5. 1 over 2 to the 5th. And I think you'll find if you multiply 2 5 times, you don't get 10. 2 times 2 times 2 times 2, 5 times should give you 1 over 32. Okay, good answer there. This is what we're looking for, changing from the log form to exponent form. Number 7 doesn't look quite as neat because the base isn't shown. And as we said back in the rules back there, that the base isn't shown, it's understood to be 10. So what we're saying is then the log of 10,000 equals 4 is the same as saying base 10 raised to the exponent 4 equals to 10,000. And I think you'll find that certainly true. Obviously 10 to the 4th, the one with 4 zeros, looks kind of nice. Okay, that's a good answer for us. 10 to the 4th equals 10,000. Natural log of e equals to, natural log of 1 over e equals to negative 1. Let's change this natural log to what we had back here. Natural log is log base e. Let's do it that way, okay? In which case then, even though this is written backwards, you might say, above here we had equal to 4, now we have it reversed. The same situation applies. We're going to say here the base e in this case, with the exponent negative 1, it should equal to this number, 1 over e. And just as we saw up above here, number 3, certainly true, isn't it? E to the negative 1 is 1 over e to the 1, or 1 over e. Same thing applies for number 15, but 15 we're going to use our tables for in just a minute, okay? Remember, this is a natural log. I'm going to change the natural log to log base e just for a moment here. And then we'll go back and check to see what that value is, okay, from our tables. The author doesn't ask you to do this, but I'd rather have you do this to get accustomed to the tables, okay? Based upon natural log being log base e, we're going to say this is the base e raised to the exponent x is equal to the number 5. Right there, okay? This is the answer the author will be looking for number 15. And notice I'm doing some of the odd ones here, asking you to probably do the other odd ones. You can check all of these in the back of the book if you like. Let's go back and let's find what this was, okay? The natural log of 5. By the way, there's our answer for number 15. Natural log of 5. Now, if you've copied the tables, you'll again see the log table here. The log table goes from 1 to 5 and also from 5 to 10. That's all we need for all the numbers in the world here. And the natural log table does the same thing. Be careful which table you're using, okay? It does make a difference. And the natural log table also goes from 1 to 10. There are trig tables that have these attached. In your case, we'll get those later when we talk about the trig. And then you'll need the e table also, okay? The e table is there separately. So here we're looking for natural log tables. And that's the second table here. And it proceeds to go down for the natural log of various numbers here, 1.0 to 5.5. And then you see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for example, let's say we're looking for 1.0, that'd be 0. 1.01 would be 0.010. 1.02 would be 0.020, etc. to 1.09, which would be 0.086. After 1.09, 1.09 comes 110 if you would, or 1.10. And that's over here to 0.95. And then 1.10 1 is 0.104, etc. It's basically a two-page table. So we're looking for log of 5. Log of 5 is down here, log of 5.0. Log of 5.00 should be 1.609. So actually, we could find the value of this. This is what the author is asking for. Go back and change it to the exponential form. But actually, the answer for this, what is the natural log of natural log of 5? 1.609, I think we found in the table there. Now that should be our answer when we're looking for that a little bit later. 1.609 for log of 5. What we're saying is this. We're saying e to this 1.609 should equal to 5. E is approximately 2.71828, on and on and on. And that raised to the 1.6 power, it should give us approximately 5. Now these are approximations now again. Consider that if this was almost 3 there, if that's 3 to the second, that'd be 9, wouldn't it? So it's almost 3 to the second, just about 9, a little bit under 3 to the second, or 2.7 to the 1.6, should be a good approximation for 5. That's actually what we're talking about there. The last one that we're doing this direction is number 19. Number 19 isn't quite as nice, it isn't as obvious as the ones above here. We'll play with it anyhow. We're going to change from this log form to the exponent form. You should understand again it's log form even though it's written behind because of the log. We're going to say of log form this base y raised to this exponent. Remember a log is an exponent. Raised to that exponent x should equal to this number, and this number in fact is x plus y. Okay. So that's what we're looking for as the answer for this one, changing it from one form to the other. And not very satisfying, we can't really check that as we did some of the others to see if it's true, but that should be a good answer for us. Okay, that's number 19. We're going to proceed with some of the others here. I need to erase this first. We'll go to 23 after this and go the reverse. 23 is going to ask us to do the reverse of this, to proceed to go from the exponent form to the log form, okay? Let's see if we can get some of this off first. Number 23 says that 78,125 equals to 5 to the 7th. We'd like to change that to log form. 27, that 8 over 125 is equal to 2/5 to the 3rd. You could probably check these if you want to multiply 5 7 times. Check to see if that's 78125. This is pretty obvious. 2 cubed is 8 and 5 cubed is 125. That's easy enough. After 27, 31. 31 is e to the x equals 6. And we'll use our tables for this one also in a moment, even though the author isn't asking us for that. 36 is a nice easy one. We'll see what that's all about. That's log base 5 of 1. And this time the author is asking us to find what this is in fact. And after 36, maybe going to 38. And 38 is log base 3 of 729. And give you quite a few examples here because I'm not really sure what background some of you have in logs. Some people studied it intensively, some haven't. So I think this will be a good review for some of you and maybe a nice intro for others. It depends on what you know here. We're going to change this from the exponent form to the log form. I say exponent form, it's exponential form. We really abbreviate that usually to exponent form. And logarithmic form, we usually abbreviate that to log form. You can tell it's exponent form, there's no log. We're going to change log. We're going to say that this is log with what base? You should understand the base here to be 5. and that's equal to what exponent? The exponent 7, right? There's only one place really for the 78,000 to go, and that's right here, 78,125, okay? So 78,125 equals 5 to the 7 can be changed from a log base 5 of 78125 should equal to the exponent 7. Same thing for 27. 27 log, this time the base, a fractional base, 2/5. Sometimes the authors will put fractional base in parentheses there to highlight it to show you what it's all about. And that's equal to, of course, our exponent 3, and the number then 8 over 125 should go right here. And again, sometimes that's placed also in parentheses, just to set it out, to make it a little bit easier to read there. So we're saying that 8 over 125 equals to 2/5 to the third power is the same as log of base 2/5, of the number 8 over 125 should equal to the exponent 3. And this one, we're going to change e to the x equals to 6. We're going to say this is log with a base e, base is e, of the exponent x out here, should equal to 6. Let's see if that's true, okay? E to the x equals 6, log base e of 6 equals x. Is that the case true? Is this base e raised to this exponent, the logs in exponent, equal to 6? Sure. Okay. This log e6, as we saw before in the other problem, same as natural log, isn't it? We could actually change this one. The author might. It's 31. You might want to check to see if the author changes log base e to natural log. That's kind of customary. Natural log of 6 equals to x there. Let's see if we can find what that is, okay? I think a few moments ago we just found the natural log of 5. Let's see what the natural log of 6 is, okay? Natural log of 6, you should be able to go back here to our table. And again, use the proper table, please, not the common log table, but natural log table. The natural log table goes to 5.5, at least on the first page. Whether if you print it back to back, you'll have the second page in the back there. If you print 2 pages, then the second page here. The second page is 6.0. Looking at 6.0 maybe as, how about 1.792? That sound okay for us? 1.792? I'm going to say the natural log of 6 is equal to 1.792. Again, not something the author is asking for. Author asks you to stop there at x equals natural log of 6. But nice to go a little bit further if we can, and so we can use the table here. To get accustomed to it, we'll be needing to use that later on for one of the next session, and also maybe even for this session. 36 is nice, really nice. This time the author is saying, look, evaluate this, find the value of this, okay? So what you might want to do first is to set this equal to some letter, x, y, z, whatever you like there, and then go from this log form to exponent form. Actually, we could use this change of base situation right here. We could use that at this point to find out what this is. I'd rather instead go ahead and just see what happens based upon what the author is looking for. Maybe we could also use the tables in a minute to see to cross-check to see if it's true. Okay? But in this case, we'd say it's log form. Let's go the reverse. Let's get it back to the exponent form. Okay? The exponent form would say this 5, that base, raised to this exponent. A log is an exponent, remember, should equal to that number. 5 to the x should equal to 1. In fact, 5 to what power is equal to 1? 5 to the 1 is 5, 5 to the 2 is 25, 5 to the 1/2 is square root of 5, and none of those will give you 1, except 0, right? How about x equals 0, okay? I think that's going to be true here. And what we could say is this, just change that x, if you would, to a 0 there. And say that actually the log base 5 of 1 is in fact 0. Is 5 to the 0, 1? Absolutely. Okay? We could find that out also by way of a table if you want, maybe by way of our log tables. Let's just see if this is true. Remember we said that our answer for x is 0 here. That's our answer. Let's proceed to look at log base 5 of 1 this way as log of 1 over log of 5. And again, for just a moment, consider that's true. We'll find out why it's true in a minute when we look at the derivation of this. But if that's true, if we could say log 1 over log 5 this way, if you look at your common log tables, again, give us a chance to use the tables here. The common log tables are the first ones here, And if you look at 1.0 here for our common log, 1.0 turns out to be a 0.0000. And the log of 5, a log of 5 is again about quite a bit down the page here. Log of 5 is 0.6990. 0.6990. And actually, you really don't care what the log of 5 is as long as it's not 0. How about 0 divided by anything? 0 divided by anything except 0 should be 0, shouldn't it? So we can do this two ways. One is a longer way for us right now, is to proceed to use the tables. But we can use the tables also to find 0. Better, I think, to go back to the exponential form and find 0 this way to say 5 to what power is 1? 5 to the 0 power. Get 0 is a good answer for us. Let's try the same thing for 38. It might not be quite as easy for 38. Let's call that equal to y, okay? And then we'll proceed to change it from the log form to the exponent form. I would normally ask you, how do you know it's log form? And you should be able to say, look, there's an log, right? Okay, we're going to say this base 3 raised to this exponent y should equal to this number 729. And just as in the previous session, session 18, we were checking to go back and forth with the exponents. We should do the same thing here. If, in fact, 3 to some power is 729, that'd be very nice. If it isn't, then we have a way of doing this, and this is really the reason for introducing logs and even inventing logs, is to solve problems of this nature. Let's say 729 was not a power of 3, then we have to have some approach to it to find some exponent for y which would approach 729. And we'll use logs to do that, okay? We'll do that a little bit later on in the session here. But for right now, let's check to see, okay? I'm thinking that 3 times 3 times 3 times 3, you kind of know that. That's 9 times 9, which is 81. And I might try another 3 there. 3 there times 81 sounds like about 243. 24 times 3. And then maybe one more 3. And that looks like 9. And looks pretty good. I think that's 729, if I'm not mistaken. So I proceed to say that 9 times 9 times 9, or 3 to the 6th, I think, maybe it's 3 to the 7th, we'll check in a minute here. It looks like 3 to the 6th might be a good answer for us for 729. Let's see if that's true before we push on. We're going to go ahead and say 9 times 9 is 81. And what's 81 times 9? 81 times 9, 9 times 1. And 72 looks pretty nice, doesn't it? Okay, so I see then 3 to the 2, 4, 6. This is the same as 3 to the 6th, and then y is the same as 6, isn't it? So our answer for this, because we're saying that log base 3 of 729 is equal to y, we're finding y is 6. We have the same bases, so we're going to match the exponents. Y should be 6 then, and that's a nice answer for us. The log base 3 of the number 729 should equal to 6. And by the way, too, even if we were using a calculator, you would be able to find this on a calculator. You'd have to play with the rules anyhow because the calculator is base 10, and here we're talking base 3. So we'd have to know something about logs anyhow, even if we were using a calculator. Okay, now that should do a good job for us for 38. We have a couple more, in fact, maybe a handful more to do on this page, and then we'll say we'll be finished with this. Let me get this off the board first, and then we'll get the last portion of page 302. Page 302 is an intro to the logs, and the changing back and forth. And then the applications and the more serious applications of logs will come on the next page on page 312. And if you haven't already done so, there's an applications worksheet that you should be using for I think maybe session 20 or 21 coming up here. So you might want to copy that off the files too. Because we're doing this online, I had to put most of the files, or I would normally pass out to you as handouts. Those had to go into the Canvas files. So you see quite a few files here. Take a look for them though. I think you should find them all. If you don't, let me know, and I'll be happy to point out where they are. Well, we finished 38, we're looking at 40 next. 40 log 10 to the negative 2, and 42 also log base 1/7 of 2401. Forty is a nice, easy problem, actually, and hoping that maybe you can give me the answer for that by looking at it. If you can't, that's okay too, but it'd be nice if you could consider that negative 2 should be an answer for us. I think, let's check to see. Remember that there's no base here. We can probably approach this two different ways. If we're taking this to a power, we had a rule back here that said taking to a power meant we'd keep the base and multiply the exponents. So actually, the negative 2 will come out front here to be multiplied with log of 10, negative 2 times log of 10. And we're talking here that log of 10 should be 1, shouldn't it? Because this base 10 understood to the first power should in fact be 10. So if that negative 2 comes out front, and we're looking at log of 10 as 1, negative 2 times 1 should be negative 2 as an answer here. But you don't have to do it that way if you don't want to at this point. If you can, that's nice and quick. But if you don't know that, let's put our log base 10 there and say, let's let this equal to another x, I guess, and let's see what happens, okay? This is again log form, log. We're going to say this base 10 raised to this exponent x right here should equal to this entire number 10 to the negative 2. It's pretty obvious the answer here. You notice that in the previous session we said if the bases are the same, the exponents have to be the same. So if the bases are the same here, the exponent's x negative 2, and x was this entire log base 10 of 10 to the negative 2. So our answer is negative 2. And we could have had that the other way by pulling the negative 2 forward and noting that that negative 2 times 1 is also negative 2. So either way, we get negative 2 on this way. Number 42 has a fractional base there. Let's call that equal to y here and say 1/7 to the y is equal to 2401. And just as we saw in the previous situation where we had that 729, which was 3 to whatever power, 3 to the 6th, we could try the same thing here. You might want to do this first though, because 1/7 is kind of an interesting base. I'd probably rather you deal with a whole number if I could. How about saying this is 7 to the negative 1? Does that sound okay? Again, we'll use our negative exponents to help us out here. And then this is 7 to the negative y, isn't it? Okay. The negative 1 times y. I'm going to check to see, is it possible that 7 to some power is 2401? I'm hoping that's the case. If it isn't, we'll just proceed to take the situation a little bit further and take the log of both sides at this point. But I think that might be the case. I'm hoping. I know 7 to the 2nd is 49. 7 to the 3rd, I'm not sure about. We can check on that. How about 7 times 7 times 7? Okay, that's 49 times 7. 9 times 7, 63. That doesn't quite make it. How about 49 times 49? Instead of 7 to the 3rd, how about 7 to the 4th? Okay, and I'm asking you to try this without a calculator because it's kind of good experience, and the numbers aren't going to be that large that you can't spend a bit of time to see what answer it might be. Let's try 7 to the 4th, okay? This would be 49 times 49. And 9 times 9 looks like promising 81, okay? 49 times 49, a 1 and an 8 there. 36 and 8 looks like 44, I think. 6 and 36 and 3 more is 16, 19 maybe. How about 1, 0 and looks like a 4 there. And a 2, how about that? Looks good, okay? So instead of 3, let's maybe change that to a 4. And how about 7 to the 4th? That is 2401. Didn't take us too long to get to that. And then if that's the case, just as above here, if the 7s are the same bases, then we can match the exponents, and negative y would equal to 4. And again, be careful with your minus signs. And negative y equals 4 means that y equals negative 4, doesn't it? Okay? So y is negative 4 should be a good answer for us. And this negative y equals 4 and y equals to negative 4. Or in fact, since there's really no y here, this entire function here of log base 1/7 of 2401 should equal to negative 4. So what we're saying is, we're saying that 1/7 to the negative 4, or when you reciprocal there, 7 to the 4th, should equal to 2401, and it does. After this, for 48, 50, and 54, we won't be able to apply the same ideas here of trying to match the bases. The base is here, e, base is 10. 10 to no power, and the whole power is 380. 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. So in either case, for all three of these, we're probably going to have to use the tables to find out what our decimal answer is, okay? We'll have an approximation. And I'm hoping if you finish with this, because I need to kind of erase some of this to get to the natural log of 29 there. Let me get rid of that if we could. And from the natural log of 29, again, be careful to use the proper tables. We're going to proceed to use the natural log tables, but the natural log tables only go to 1 to 10. And even at that, though, it might sound, well, they're very limited. They're limited to one respect, but they can help us for all the numbers we want. Once we change this to scientific notation, okay? Just break this 29 down a bit. It takes a little bit of time, but not too much. I hope you'll agree with the natural log of 29 is a natural log of 2.9 times 10, isn't it? 2.9 times 10 is 29. And then since we're multiplying these, we're going to say when we multiply the numbers, the same as adding the exponents that we talked about in the rules back there. So how about the natural log of 2.9 plus the natural log of 10, okay? When we're multiplying the numbers, the same as adding the exponents, and the logs are exponents. So how about the natural log of 2.9 plus the natural log of 10? Natural log of 2.9, and from your table again, use the natural log tables here. I'm looking at 2.9, 2.9, and then over to 0, looks like 1.065 for that. 1.065, let's see if that works for us. 1.065. The log of 10, I think, is 2.303, if not mistaken. And if you add those two together, I'm getting 3.368 for this. And that should be a nice number for us. What we're saying basically is, remember, natural log is log base e. Let me maybe change that a bit. Log base e of 29. It should equal to 3.4 roughly there, 3.4. What we're saying is this e to the 3.4, or 2.718 to the 3.4, should come very close to 29. That's what we're saying there. And this cannot be done anyway by matching the bases. We have to use a table for this. And we get an answer then from the table by breaking it down. 29 to 2.9 times 10, or 2.9 natural log of 2.9 plus the natural log of 10. Inserting those values, 3.368. If we're testing for this, I'd ask you maybe to give me 3.4, 3.3, 3.368. You get from the table very nicely, but these are approximations, so I'm not going to say, well, you know, you're off by the thousandths plate. That's not what we're looking at here. Asking to make sure that you can handle the information there and know how to make the conversions, use the tables. This is what's important. The decimals are nice to get. If you told me 33, I'd say that's a bit off. You know, come closer than that. 3.3, you missed the decimal there. Be careful with the decimals and the signs, but don't worry too much whether it's 3.368, 3.36, 3.35, somewhere around there, or just 3.3 or 3.4. We'll do the same thing for the common log, okay? For the common log, we're going to change this by making it, again, scientific notation, the log of 3.8 times 100. Log of 3.8 times 100. And instead of times 100, I would say plus the log of 100, okay? So if you multiply 3.8 times 100, you should get 380. You should know that 100 is 10 squared, isn't it? And I think we just finished a problem with this above here with the negative 2. The 2 will come out front, and the log of 10 is 1. So basically the log of of 10 squared is nothing more than 2, isn't it? And then looking for the log of 3.8, that'd be on the first table here, this time common logs tables. Trying to give you examples of both common log and natural log. The common log here, 3.8. 3.8 out front is maybe right in here. And I'm looking for something that looks like 0.5798. 0.5798. And add 2 to that, and how about the answer is 2.5798. And a nice answer for us, okay? You could press the calculator, get the number a little bit faster, but then again, you wouldn't be learning how to use the table, would you? So, break it down just a bit, with the scientific notation, 3.8 times the 100, and break that down a bit each time, find the decimals, you're on your way. How about this as changing to scientific notation for number 54, the log of 3, and then a plus, or times I should say, 10 to the what? 10 to the 1, 2, 3, 10 to the negative 4, is that right? How about log of 3 times 10 to the negative 4, or log of 3 plus the log of 10 to the negative 4. Would that be okay? And that's the log of 0.0003. Again, if you're talking 3 and 4 decimal places to the left, 3 and 1, 2, 3, 4. Looks pretty fair. That should work for us. The log of 3, well, first of all, maybe the log of negative 4, okay? Log of negative 4, just from above here, that's 10 to the negative 4. The negative 4 comes forward. So we're looking at negative 4 for this one. Negative 4. And then plus, if you would, there. And the log of 3. And the log of 3 from, again, the front of the table here. Log of 3 looks like 0.4771. 0.4771. And be careful on this one because it's actually 0.4771 plus a negative 4. And maybe a negative 4 if you would, 0.0000. Okay? So really we're going to subtract these two. Put the negative 4 on the top side there so it's easy to subtract. Negative 4 and then the positive 0.4771. Subtract those, and I think we're looking at probably on this one, maybe, let's see what we should have there. How about negative 3.5229? Negative 3.5229. I think that'll work for us, okay? Check to see if that's true. We could probably fit it right here if you wanted to. Maybe, let's try that. Negative 4.0000. And 0.4771. We'll have to borrow in each case at the 10 and 9 and 9 and 9 and 10. 1 from 10, 9. 7 from 9, 2. 7 from 9, another 2. 4 from 9, 5. And that became a 3. How about negative 3.5229? Looks pretty fair. Okay? So again, a bit of arithmetic there. When you finish the course, you'll be very good at arithmetic. Your friends will be amazed at how quick you are with this. And we've also done a good job with the logs. Okay? I think this finishes page 302 for us. We're going to look at page 312 next. And 312 is kind of interesting. It's kind of a combination of the previous section there on changing the bases and the exponents and the various forms, and also playing with the logs, okay? So might be a nice way to end the session here to kind of combine the previous session with this one. Page 312, and we're starting with number 2. And 2 says log of base 69 of 1. And we actually did this a few moments ago in one of the other problems. The author does a nice job of going back and always in the next section, going back and reviewing a bit of the previous one. This is log form. We could use our change of base, which we'll use in just a few minutes with another problem. But let's go back to the exponent form for now. Let's call this x, and let's say this means that this base 69 raised to this exponent. The logs in exponent didn't change from the previous page, okay? And that should equal to 1. I think we saw this with 5 prior to this, one of the other problems. 69 to what power is 1? 69 to the 0 power is 1. So x equals to 0 there. Put a 0 in here for x and check to see if that's true. Is 69 to the 0, is any number to the 0 power 1? Absolutely. 0 should be a good answer for us for number 2. Number 6. Number 6 is natural log of e to the third. The 3, as we know, should come forward because we're taking to a power. So the 3 should come forward. We're going to multiply in the exponents. This becomes 3 times the natural log of e. And natural log of e is another way of saying 1. We saw back here, natural log of e equals to 1. So we're going to change that to 1 and say this is 3 times 1, or just 3, and there we go. And that's a nice, quick, easy answer for number 6. Okay? There's 6 for us. After that, we'll drop down to 10. And 10 is kind of nice, too. It looks a little more involved, but not quite. The cube root of 5. And I'd probably change that cube root of 5 initially, and you should know what it changes to probably a fractional exponent. I know that the fractional exponent looks like it might be difficult, but probably not so. I think that the 1/3 might be nicer, believe it or not. Is that true? Is 5 to the 1/3 the same as the cube root of 5? I think that's true. And then again, if the 1/3 comes forward here, you say this is 1/3 log base 5 of 5. And believe it or not, log base 5 of 5 should be 1, I think. Let's see if that's true. Log base 5 of 5. 5 to what power is 5? 5 to the first power. In fact, when the base and the number are the same, it's always 1. So this is 1/3 times 1, better known as just 1/3, okay? So 1/3 for us there for number 10. We have just a couple others to do here. We're looking at 26 next. And what I'm going to do on 26, I think, is probably to erase the board here for you and then proceed to put the, it's a little bit longer, I think, for us. Yeah, let's erase that if we can, because I'd like to spend a lot of the board here on it if I could. The 26 asking us to do this, to break this down. 26 is log base b of R4 over S squared. And we want to use the rules just to break it down. It's not going to be very satisfying. We won't get a nice and easy number as we did in the previous problems, but it gives us a chance to use the rules here to see how they work. We are dividing with the numbers, therefore we should be subtracting the logs. So this should be log of base b, if you would, R4 minus log base b of S squared. That's what the division does for us. And then just as we saw before, the exponents will come forward here because we're going to be multiplying. When we take to a power, we'll keep the base and multiply the exponents. So we're looking basically at 4 log base b of R minus 2 log base b of S. And that's our answer. That's the best we can do. Just a matter of academically changing from the one form, the division form with log of that one big number, to the log of very smaller numbers, number 26. And we'll try another one of those too, maybe number 38, okay? 38 is just the reverse, in fact, 2 log base b of u plus 3 log base b of v. And let's proceed to do the reverse, right? It's very similar. the 2 should work its way back to here, log base b of u squared plus log base b of v cubed. And what about the plus sign? When we're adding the log, same as multiplying the numbers. So basically we're looking at this, log base b of u squared v cubed. And that should be a nice answer for us, okay? So going one way, a very large number here broken down into very separate logs, and then separate logs built back up to one large number. And that should work for us for 36. Excuse me, 38. After that, maybe 42. Another example of that. I'm looking at 42. Usually, I think one example of each of those should be enough. But I like the number 42 here because the author, again, didn't continue to do what we should do. We should proceed to simplify as far as we can. And even though you don't have 42 in the back of your book as an answer, I have 42 answer, and the answer the author gave, not quite as nice as I'd like, okay? Again, one of those things where simplified, sort of, but not as far as you should have gone. So I want to, again, caution you about that. Always use what the information you had in the previous classes to finish it. Don't just stop there and say, okay, I'm finished, and be satisfied with a rough answer. You should get the final answer, okay? For 42, we're looking at 1/2 log base b of x, and then minus 2/3 log base b of y. And then if you go back and change this to what it should be, this is log base b of x to the 1/2. And you should understand x to the 1/2 to be the square root. And then minus log base b of y. And here y to the 2/3. And I'm hoping you're recognizing 2/3 is this, the cube root of y squared. Y to the 2/3. Remember, it's exponent over index. Exponent 2 over index 3. Just as this is 1 and understood 2 there. X to the exponent over the index, x to the 1/2. And this is the same thing, x to the 2/3. And then the division here should be log base b of the square root of x over the cube root of y squared. And I think we saw this before. This is where the author stops. In fact, doesn't even use it in the radical form. Instead, uses it in the fractional form. But this is where the author stops at the answer, and we are not to do that. And you should know why you shouldn't. There's a radical in the denominator. So instead of this, you should simplify this by multiplying by 1. And I think in one of the previous problems we did this when we were in class together. It is not going to be the cube root of y squared. Instead, you want to know what is going to match the base of the exponent. And that would be the cube root of y, I think, wouldn't it? The cube root of y times the cube root of y. The cube root of y squared times y is the cube root of y cubed. And that's just y. And the numerator will stay the same. So our answer for this one, log base b of the square root of x times the cube root of y all over y. Okay, that should be, maybe some parentheses around that would make it look nice too. That should be our answer, okay? So it's a bit more involved than the others in that the author stops here with the fractional exponents, x to the 1/2 over x to the 2/3, over y to the 2/3. And y to the 2/3 is a radical. It's disguised maybe, but it's nonetheless a radical. We should change it by multiplying by 1 in this form. The cube root of y squared, cube root of y is cube root of y cubed, or just y. And this should be a nice answer for us for 42, okay? The last two are 50 and 54. And 50 and 54 are problems that are going to involve the change of base routine, okay? So I'd like to proceed maybe to give you an example of that routine. We talked about it back here, and I didn't want you to say, okay, accept that on faith. I'd like to show where it comes from. It's one of those things like maybe the division of fractions where you turn the second number upside down and multiply. You say, well, why do I do that? Well, one's a mechanical process, and there is some math behind it, okay? So I do want to show you the math behind this, some of the theory, and not just say, okay, here's the practicality, and not really know where all this comes from. So let's go ahead and play with that, okay? Let's do an easy one, okay? An easy one, something like this. How about the log base 4 of 16. How's that sound, okay? I think you'll agree that if this is the case, that should be 2, shouldn't it? Right there. What we'll say is this, let's go back and check to see if this is the same as log of 16 over log of 4. We like to check to see if that's true, okay? In other words, I would want to do it with this one is obvious. This base 4 raised to this exponent 2 is 16. If I had some other number here, like a 5 or a 7, then I might want to change this base, because it'd be a little bit easier for us. We use base 10 on our log tables. But let's see if that's true, okay? Let's go back from this form to the exponent form. 4 to the second equals to 16. Agree with that? If we took the log of both sides, log of 4 squared equals to log of 16. And let's proceed to maybe put the 2 out front there. In fact, let me do this instead. Let's not even call it a 2. Let's call it an x for a minute, okay? Let's just call it an x. It might be nicer if we'll follow it that way. Let's call it an x, okay? The same thing would occur. This would still be log of 16 over log of 4. But let's see if we can get the x by itself to be the same thing right here, okay? If we took the log of both sides, log of 4 to the x equals to log of 16. And then if we proceed to put the x forward as we've done before, this is x log of 4 equals to log of 16. And then if we divide both sides by log of 4, guess what? X is log of 16 over log of 4. So another way of writing this, if I proceed with some transformations by way of the exponent form and then log of both sides, and guess what? I could just as well have said log of 16 over log of 4, okay? The same thing. So instead of doing all of this, the math of it actually, the mechanics is draw a line, log of 16 over log of 4, and there you go, okay? So instead of doing the math, which I've shown you here, we'll just go through and do the mechanics of it here, save a bit of time for us, and we'll get a nice answer, okay? Let me erase this, I need the space for the next 2. And we'll use that change of base routine then to our advantage, to change from the usually a different base to a base 10. Believe it or not, there are tables with different bases, maybe stuck away in the library somewhere there, that you probably have a difficult time doing this with a calculator and changing the base on that, okay? It's usually structured for base 10 or base E, the natural log. Very few calculators can be changed to other bases. We're going to try 2 examples of that with change of base, numbers 50 and 54. Number 50 here is the log base 4 of 19. Log base 4 of 19. And again, had that been 16, no problem. Unfortunately, it isn't 16. So it's not going to be 2, it's going to be 2 point something, I would guess. Let's call this x. The change of base is really simple. There it is right there, okay? So our problem becomes log of 19, log base 10 of 19. By the way, we could have changed to any base we wanted, but base 10, of course, is the usual one for us. And we'll look for log of 19. Log of 19 is log of 1.9 times 10. That's over log of 4. This is log of 1.9 plus the log of 10. You should understand, maybe I can draw it out here. I don't really want to, but I guess I'll have to. 1.9 plus the log of 10. You should know the log of 10 is 1. Log of 1.9. Log of 1.9 I find as 2.788 plus the 1, and log of 4, and it should be 0.6021. 0.6021. Let's see if that's true first. We know the log of 10 is 1. 10 to what power is 10? 10 to the first power, that's a 1. 1.9, this is common logs now. 1.9 down here, about right to there. 1.9 looking across in the first column, 0.2788. 0.2788. This is going to be 1.2788. And looking for the log of 4. Log of 4 is about right here. It's 0.6021. 0.6021. I would not expect you to do this division. I would not expect you to divide by 0.6021. I ask you to do some rounding. That's part of the course too. And this rounds off to 0.6. Good enough, okay? Now had it been 0.6521, I'd ask you to change it to 0.65, okay? Because 0.65 is about halfway between 6 and 7. be a little more accurate than just 0.6. But in this case, 0.60 is good enough as 0.6, okay? Move it one place in either direction here, both above and below, one place to the right. Basically, it's 6 and a 12, which is 2 point, and maybe a 1 and a 3. That's good enough. You know, 6 goes into 7 once and 1 left over, 6 and 18 3 times. 2.13 is great. Very nice, okay? Good answer for us. That'll work. What we've done is use the change of base routine to change log base 4 of 19 to log base 10 of 19 divided by log base 10 of 4. We've simplified 19 to 1.9 plus log of 10, and I arrived at the various numbers by way of the tables for this. Did some arithmetic, and there we go for number 50. Again, I need the board space here for number 54, so I erase this. You can always proceed to go back to your stop it here and look at it for a while, and then come back afterwards to replay it. Let's get the last one here, 54, and we'll see we've done this session and done a good job on it. We have just one more session to do before we look at our application sheet, and then after that, then we're just about finished with this chapter, believe it or not. It's a very quick chapter, and logs are fun anyhow. They're kind of quick. They're supposed to be quick because they're a nice quick way of saving time for us when we deal with some of the exponential problems. The last one I want to deal with is the decimal one, and this is log, this number 54. 54 log of 2.5 with the base of 7.2, okay, base 7.2 there. And we're going to call that equal to x, if you would. And say this is log of 2.5 over log of 7.2, okay? And actually, even easier, believe it or not, than the other one, because we don't have to do any changes here. We can use our table directly for this one. Now, using your table directly, we're looking at the log of 2.5, and log of 2.5 is about in here. I'm looking at 0.3879 on that one. 2.5. 2.5 is 0.3979. 0.3979. And after that, looking for maybe the log of 7.2. 7.2 is in the back, well, on my back side, and yours, it'll be maybe the second sheet if you didn't print it back to back. Looking at 7.2, 7.2 is about here. I'm looking at 0.8573. How about 0.8573, okay? And this is something like what I referred to the previous problem, that I probably ask you again not to do the division here. Don't want you to do log division with 4 places here by hand. Instead, ask you to round this. We could round numerator and denominator, but I'm not asking for that exactness. Just go ahead and use the 0.3979. And this time, maybe ask you to round it off to 0.86. And this is actually in class, I would stop and say, what would you round it to? And hope that you'd see that 0.8 would be too rough an answer. 0.85 would be better. And because it's 7 here, I'd say 0.86 would be nice, okay? Move this 2 places above and below. Let's go ahead and do that. Let's call this an 86 and divide it into 39.79, okay? Let's do that. Move it 2 places above, 2 places below here. Unfortunately, 86 will not go into 39. It broke on to 397. I'm going to guess probably about 4 times. Okay, let's see if that's true. 4 times 6 is 24 and a 2 there. It looks like 34. When you subtract that, that's a 3 and a 5 there maybe and a 9. And how about a 6 on this one, okay? Let's give a 6 a try and see if that'll work. And 6 times 6 is 36. And a 3 there, and 48, 51. That's good enough. We could continue a little bit further on that. I know that 16 isn't the same as 39, but that's good enough for us. 0.46. You might check, these are even ones, and you might check the back of the book for the odd ones when you get them by the table to see how close you come with what the author gives by way of a calculator, okay? I think you'll find it's pretty close. It's kind of a nice answer we get with a small little table here compared to the author's calculator. All right, this will do it for session 19 for us. We discussed the fact that, most importantly, as usual, logs an exponent. We looked at the various ways of changing from the log form to the exponent form and the reverse from exponent form back to log form. We also indicated that there are rules for the product of 2 numbers. We'll say that when you're multiplying the numbers, same as adding the exponents. So log of x, y is equal to log of x plus a log of y. Division of the numbers is the same as subtracting the exponents, log of x minus log of y. And taking to a power, we will put that y out front, and it'd be multiplying the exponents. And then a little change of base situation here. And two rather important items too, that log of 10 is 1, and that the common log of 10 is 1. And the natural log of e is also 1. That should do it for this session. Again, print your tables, you'll need those, and get those from Canvas. We'll see you for session 20.